Hello students, in this video we'll give our first example of a family of conformal maps, the simplest ones, namely the affine maps. While they're trivially conformal, let's investigate exactly what they do and see how the curves maintain the angle between two curves under these transformations. So we're going to consider affine transformations in this. Of C, okay? So affine transformations of C. It's the simplest type of conformal mapping, right? So let's consider the mapping W is equal to A capital of Z plus B capital, where here A and B are complex numbers. These mappings are called affine. Okay. And of course, what's happening over here is these affine maps are basically, let's assume that B is not 0, right? So if B is equal to 0, it's a different situation, but they're the composition of two mappings, right? These are the composition of two maps. Okay. And what are these two maps? The first thing we're going to do, we assume that A is not equal to 0, right? A is not equal. I'm going to assume that neither of them are 0, just for simplicity, okay? So if they're 0, then you get the silly cases, right? So let's look at this one over here. Let's do phi 1 of Z. What's this phi 1 of Z going to be? It's just, I'm going to multiply, I'm just going to shift. It's going to be Z plus B over A. And then phi 2 of Z is just going to be multiplied by A, right? It's just going to be A times Z, right? And so phi 1 and phi 2 are separate classes of functions, and every affine map, then this implies then W is equal to phi 2 compose phi 1 of Z. Let's check. That's phi 2 of what? Of Z plus B over A. And that just multiplies by A, so that's going to be A times Z plus B over A, which gives me AZ plus B is exactly what I wanted. So in other words, it's the what? So affine maps are the composition of a pure multiplication by a complex number and a translation. So hence affine maps are compositions of translation and scaling. Complex scaling. And it's complex translation as well. Good, okay? So let's analyze the roles, what happens with phi 1 and phi 2, right? So the first thing we're going to do, we're going to take a region. Let's figure out what happens over here. So let's do an example, right? And so let's analyze phi 2 carefully. So here's a proposition. Phi 2 mapping C into C does what? Rotates a point, points by argument of A, and scales the points by modulus of A. Okay, good. All right, and how do we prove that proposition? It's relatively straightforward. Proof of this proposition. Well, what's going to happen over here? So we're going to write Z as R e to the I theta and A as what? So A, Z is really modulus of A e to the I argument of A, and then R e to the I theta, where that's what Z is, right? And so this is going to be R hit with modulus of A, so you're scaling the modulus by A, and then you have e to the I, and then you have a theta plus argument of A. So what are we doing here? This is a rotation over here, right? So that's a rotation, and that's a scaling. So this is rotation and scaling. So it's this is a scaling, of course. Scaling times a rotation. Two operations in a row, okay? Scaling and rotation. Good. All right, and so now let's do an example. And of course, what's this going to do? So whatever B is, you're going to what? And then the proposition 2, I guess, would be the following. Proposition phi 1, mapping C to C, translates by real A in the real direction, real B in the real direction. And imaginary part of B in the imaginary direction. Excellent. All right, let's do an example of this. Here's the sort of the classic example of what you want to do. So here's an example. Let's find the image of the square with vertices 0, 1, 1 plus I, and then I under the map W equals 1 plus I, Z plus 1. Okay? So let's do it. Here's 0. Here's 1. Here's 1 plus I. And then here's I. And there's our square, right? Okay? And the complex plane. So what's going to happen? Let's take this one first. The first thing we're going to do, let's do this operation first. I'm going to do the scaling operation first, okay? So the first thing I'm going to do is I'm going to say, okay, well, what's 1 plus I? 1 plus I, Z, is really the square root of 2 e to the I pi over 4 Z, right? By going polar form. So this is going to scales by root 2 and rotates by pi over 4, okay? We can easily just check, right? So this point 1 is going to get mapped to where? This point 1 is going to be mapped exactly to 1 plus I. So this 1 is mapped over here, right? The 1 plus I is going to go to what? The 1 plus I is going to go to 2I, right? Like that. The I is going to go to what? The I is going to go to negative 1 minus I. Negative 1 plus I, rather, like that. And so we're getting all these loops over here, so let's do it carefully, right? So we're just doing this stretch and rotate. So I'm stretching and rotating, okay? So what points are we going to have that are new? Let's draw it. So of course 1 is going to go to 1 plus I. So this is the point, let's call it point 1. So 1 goes over here, right? And then where does 2 go? We can just plug it in. 1 plus I squared is going to be what? If I did 1 plus I times 1 plus I, that would be what? That would be a 2I, right? Because the I squared is negative 1. So that's going to go to 2I up here. And then what? And then the point I gets mapped to where? 0 gets mapped to 0 still. And then where does I get mapped to? It gets mapped to I minus 1. So negative 1, and then I, like that. So our square gets like this. It's still a square. Of course, this is not to scale, but this is still a square. It's just been rotated and stretched out, right? So each of these lengths now is root 2, root 2, root 2, root 2, root 2, right? Good. Okay. And then finally, what are we going to do? We're going to pick it up and move it 1 unit over, right? So pick it up and move it 1 unit over by the rotation, and where do we go? We go over here. Here's the real axis. Here's the imaginary axis. Okay. And so the 0 goes to 1. The 1 plus I goes to 2 plus I. Then this point over here, the 2I gets mapped to 2I plus 1. And then over here, that last one over here is going to get mapped to what? Get mapped right into the axis over there, because I add 1 to it, okay? And so we get this square. Okay, so it's still a square. The side lengths are still root 2, root 2, root 2, right? This point now, of course, is what? That's 2 plus I. This point over here is 1 plus 2I. And this point over here is just going to be a 2I, not a negative 1 plus 2I. So it maps a square to a square, and we can sort of see why this is conformal. So just a note, this is certainly conformal. This is clearly conformal. Everywhere. Conformal. Why so? What's the derivative of this? That's the easiest part, right? That's the easy part to prove it conformal. Prove it's conformal. What's dw dz? dw dz is equal to a, and by assumption we assume that wasn't equal to 0. So the derivative is a constant, it's definitely conformal, right? So in other words, it would just see what happens in particular when we work with these squares. The best way to handle conformal mappings is to understand what happens to some very simple geometric figures. So whenever I think about a conformal mapping problem, I try to think of a very, very simple figure that I can I can figure out what the transformation is doing on that simple figure. In this case, a square is very easy. I know how to rotate a square by 45 degrees. I know how to stretch a square out. I know how to shift a square. Very, very easy from like high school geometry. That's why I chose a square, for example. I didn't want to choose something like a parabola, where it's going to be much more complicated to rotate the parabola. Do the simple cases to get a good handle under the conformal mappings. In further videos, we're going to extend our families, right? We've done linear maps now. We want to figure out how to do more complex conformal mappings, and in particular, we want to handle conformal mappings in the case when there might be a spot where the derivative is equal to 0 and try to analyze what happens in the neighborhood of that 0 point. Thank you very much.